Hello again. At the end of the last video, I gave you this question. This shows what would happen. This will illustrate what would happen if you change alpha. When you change alpha to 10%, the z-value becomes 1.64. Then, using the same formula, just change this number. All the other numbers are the same. Change these numbers, then you get this. So compare 80.82 and 79.18. Previously, it was 81 and 81 something, 78 something. So when alpha was 1%, your confidence, your critical values are wider, further from your belief. But when you increase the alpha to 10%, it shrinks because you are going to reject more by increasing the significance level. To do that, you have to shrink the acceptance region. So it becomes tighter. They are closer to each other. So now, after increasing the alpha to 10%, your sample mean is now outside lower than the lower critical value, right? So it's here, this is smaller interval is your critical values, and your observation is now here, right? Outside the smaller, lower critical value. So your observation is on the rejection region. You have to reject the null hypothesis in this case. So as I repeatedly say, increase in alpha makes more rejections, right? Reject more. So this is another example. And by the way, if you compare what we have done so far, no matter what method you use, the rejection and acceptance rejection is the same, right? If it's 10%, you should reject the null hypothesis at 10%. You should reject null hypothesis like this in p-value approach, t-statistic approach, and the critical value approach. Right? They have to have the same results. And like if you change 1%, you don't reject null hypothesis, but same for all three methods. Otherwise, something is wrong. So you may use different methods as a double check if what you have done was correct or not. Final numerical example here. So far, we used the null hypothesis that I-beams are correctly sized. But suppose that you believe that the manufacturer, the I-beam manufacturer, is making it a little bit smaller. So consider null hypothesis that your belief is already 78 millimeters, which is smaller than 80 millimeters. And let's see what happens. The data are the same. I do not change the data at all. 400 observations, and the sample mean is 79, and the standard deviation is 10. Then, can you reject the new null hypothesis, this null hypothesis at 1%? You may choose any method. You may use p-value, t-stat, or critical value. Just get the answer. Or whatever method you use does not matter. Choose whatever you like and make the decision. It may take more time, so stop the video. And when you finish the work, come back, watch the answer. 3, 2, 1, turn. So I gave you all the three methods. T-statistic, if you use t-statistic, you get 2. You get 2, t-statistic equals 2. And at 1%, you have to compare this with threshold 2.58. And p-value, if you use p-value using this t-statistic, it's 4.55. If you use critical values, 1% uses 2.58. And the belief is 78. So around 78, you allow this much marginal error. So you get these two numbers and compare these critical values with the sample mean. So what you see here is at 1%, the t statistic is within the plus minus 2.58. So t statistic lies between plus minus z values, so it is not rejected. P value is greater than 1%, so it is not rejected. Critical values contain the sample mean, observed sample mean, so it is not rejected. So in all the methods, you do not reject the null hypothesis, right? So the main purpose of this exercise is to see this. So we considered two different hypotheses. At the beginning, first we considered hypothesis that mu equals 80 millimeters. And then when you use 1% significance level, it was not rejected. So 80 millimeters was not rejected, and which implied the I-beams are correctly sized. So 80 millimeters was the correct size, so if you use this null hypothesis and 1%, they are okay. The I-beams are okay. But later, I changed the hypothesis to 78. So now you believe the mean is 78 and use 1%, the same 1%, and same data. It is not rejected again, which means the I-beams are too small. So it says, the result says, hypothesis testing result implies that I-beams are 78 millimeters tall, which is a problem. So it means that I-beams are not okay. So the two results are contradicting to each other. So that it shows the intrinsic potential problem or nature of a hypothesis testing. So even you use the same data, the conclusion could be totally different depending on which null hypothesis you use. So choosing the null hypothesis is also very important, as we see here. And usually the basic principle is to be more conservative. So you have to put yourself in the handicapped position. So the existing belief should be put as the null hypothesis, and it will be favored, and put your argument as the alternative hypothesis. That's a very interesting feature of interesting property of hypothesis testing, and somehow weird and kind of unfair analysis. Okay, I have one more numerical example to show you, and I'm going to do that in the next video. So thank you for watching. See you in the next video.